Okay, guys, I think we should start. This is the final lecture. Usually, on the final lecture, the amount of students is a bit higher than on the previous lecture, but this one will be an exception, as I can see. Okay, who can remember what was during the previous lecture? Who thinks that I should recall what we discussed in the previous lecture? Okay. So we actually discussed two things. We discussed the Buchberger criterion for a set of polynomials to be a Gröbner basis, and then we discussed the Buchberger algorithm, which allows us to extend any set of polynomials to a Gröbner basis, generating the same ideal. So today I want to prove those statements. First of all, let me recall the Buchberger criterion, the claim. The Buchberger criterion. Suppose we have a set of non-zero polynomials in several variables, and we have some lexicographical ordering fixed. Then the following three statements are equivalent. The statement number one, G is a Gröbner basis. The second one, for every two polynomials G and F from G capital, there exists a way to reduce their S polynomial to 0 with respect to G. And the third statement, for all pairs of polynomials from G capital, every reduction of the S polynomial gives you 0. So this is the Buchberger criterion. So if you want to check if something is a Gröbner basis, you want to go through all the pairs of polynomials, and you want to try to find a reduction of this S polynomial to the 0. And if you can find at least one non-zero reduction, you don't need to check all the reduction. If you can find at least one non-zero reduction, then this is not a Gröbner basis, and if you can reduce all S polynomials to 0 at least once, then this is a Gröbner basis. So this is a criterion. Now, how to prove this statement? The proof will consist of two steps, and the main ingredient of the proof is what's called the diamond lemma. So let me formulate the diamond lemma. The claim diamond lemma. Okay. Do I want to say something? No, I don't want to. Okay, so again, we have a set of polynomials, non-zero polynomials, and a lexicographical ordering fixed. The following is equivalent. The claim number one, G is a Gröbner basis, and the claim number two says the following. For every polynomial f, and let's say f, and for every two polynomial g1 and g2 from G capital, we may consider a reduction of f with respect to g1 and get f1, and a reduction of f with respect to g2, this will lead to f2, then there must exist a way to reduce these two polynomials to the same one. So there must exist a reduction of f1 with respect to g to r, and a reduction of f2 with respect to g to r. So there must exist, let me say like that. So for every g1 and g2, there must exist a way to reduce these two polynomials to r. So let me repeat what's going on here. So what does it mean that G is a Gröbner basis? It means that you can take every polynomial f from the polynomial ring, then all the remainders of this polynomial with respect to this set are the same. So when you reduce every polynomial and you will stop at exactly the same polynomial. And this polynomial is the unique remainder. Now, how to check if something is a Gröbner basis? So there is a simpler condition that you have to check. You take any polynomial f, and you make two elementary reductions of this polynomial f using g1 and g2, which lead to some polynomials f1 and f2. And then you have to find a way how to reduce these two polynomials to the same one. So if you can take every f and every two elementary reductions, and for any black part written like this, you can find this blue part, then this is a Gröbner basis. So this is a weaker condition. So it doesn't say that every reduction leads to exactly the same remainder. It says that, like, if you have two paths, then at least you can merge them together. This is how it works. Okay, are there questions regarding the statement of the diamond lemma? Okay. Who think that it's clear what the diamond lemma says? And who just came and want me to repeat the diamond lemma again? Okay, so for those special visitors who just came and pay attention to what's going on the whiteboard, I want to repeat the claim itself. So now we want to discuss one of the main ingredients to prove the Buchberger criterion. So we want to check if something is a Gröbner basis. So instead of checking that something is a Gröbner basis, you can check a weaker condition. So for every polynomial f and every two polynomials from G, you consider their elementary reductions, and then you should find a polynomial R and two reductions from f1 and f2 to this polynomial R using G capital. So if you can do this for every f, G1 and G2, I mean, this is what you want to do, then this is a Gröbner basis. Okay. Yep.
Should R be necessarily a remainder?
No, it need not be a remainder. I mean, you can make it a remainder, because if it's not a remainder, you can proceed with the reduction, and then they lead to a remainder.
But it's enough to find
Yeah, it's enough to find some polynomial such that these two paths lead to the same polynomial. Okay. Now, so let's prove that these two are equivalent. So we want to prove that these are equivalent. Now, how do you think which direction is easier? Which one?
From the first to the second is easier.
Yep. So from the first to the second should be easy. By the way, who can see how to prove this implication, just in case? Is there anyone? Okay, nice. Okay, so let me explain why this is true. So suppose G is a Gröbner basis. What does it mean? It means that for every polynomial, we have only one remainder, okay? Now, suppose we have this black part. So we take any polynomial f, and we consider two elementary reductions of f. Now, let's reduce f1 to a remainder and f2 to a remainder, okay? No, it's not zero, but they will be the same. Why? Because they will be remainders of the same polynomial f. But since every polynomial f has a unique remainder, so the reductions of these two guys to a remainder, they must automatically lead to the same polynomial. So that's why if G is a Gröbner basis, the diamond lemma holds by the trivial reason. Okay, who was able to follow? Okay, are there any questions? Should I repeat or explain at least something? Okay, good. Now, the interesting part is, of course, to prove that if we are given this claim, then G is a Gröbner basis. Now, suppose the second claim holds. Now, we want to prove that G is a Gröbner basis. Let's assume that the contrary holds. Suppose not. Suppose G is not a Gröbner basis. What does it mean? It means that there is a polynomial f such that it has at least two different remainders. So there is a way to reduce f to remainder 1, and there is a way to reduce f to remainder 2. So they are distinct, and they are remainders. Okay? Now, I want to take this polynomial f, and I want to consider. Oh, by the way, what does it mean that there are two ways? It means that, well, every reduction starts from an elementary reduction. So at least it starts from a reduction by some polynomial of g, and the other one also starts from some polynomial g. But let's take a look at all possible elementary reductions of f with respect to g. So I want to consider all possible reductions of f with respect to g. g1, g2, g3, and so on, gm. Okay? Now, there will be two different types of polynomials. I want to mark them as follows. So the red ones, the bad guys, and the green ones. Let me explain the difference. So, and by the way, this one will be also the red one. So let me colorize all the polynomials by two different colors. The polynomial will be red if it has at least two different remainders. And the polynomial will be green if it has a unique remainder. Okay? So it may happen that all the reductions of f are red, or they all green, or you have green and red remainders. But these are good guys, so these guys have only one remainder, and these guys are bad, and they have different remainders, at least two different remainders. Okay? Now, what I want to do, well, since I suppose that G is not a Gröbner basis, we have at least one red polynomial, and we started with the red polynomial. Okay? This is the red polynomial. Now, what I want to do, I want to find a red polynomial such that all elementary reductions are green. Okay? The aim is to find a red polynomial such that all its elementary reductions are green. Okay? This is the first step. Well, suppose, we started with a polynomial f, which was red. If the set of empty reductions is, or if the set of red reductions is empty, then we have found one. So we may suppose that here the set of red reductions is not empty. So let me rewrite this again. So now, if it's not empty, let's take one, and let's consider all of its elementary reductions. Again, let's assume that we cannot find such a polynomial, so some of them will be red, and some of them will be green. Again, if there is at least one red, we can proceed. And again, if we can proceed, we can consider all the elementary reductions. And if this is not true, we can again find red ones and probably some green ones. It's not necessary, but what is important, we always can find a red one. Okay? So if we cannot find a polynomial with these properties, then going by this road, we can find an infinite sequence of reductions. But it's impossible. We already know that if you make a sequence of elementary reductions, it will terminate. So that's why at some point we will find a polynomial which is red, but all of its elementary reductions will be green. So that's why we can achieve this aim. Who was able to follow? Are there any questions? Okay, good. So now,
Can you please tell
Again?
Why there is such?
Why there is such a polynomial? Because if there is no such a polynomial, then on every level we can find a red polynomial. So that's why for every polynomial produced here, we can find an arrow leading to a red polynomial, and so on. So we can produce a sequence of elementary reductions from red polynomial to red polynomial, and so on. And this sequence of elementary reductions will be infinite. Okay? But it's impossible to have an infinite sequence of elementary reductions. We proved this already during the previous lecture.
And a red polynomial always has a child?
Well, if a polynomial doesn't, because if a polynomial doesn't have a child, it means that you cannot reduce this polynomial. So it's already a remainder. But if you have a remainder, well, by definition, it has only one unique remainder, which is the polynomial itself. Yep. Now, is it okay? Or is there something that bothers you?
No.
Okay, good. Now, now we want to consider this case of this polynomial f, which is bad, but all of its elementary reductions are good, let's say. Now, what does it mean that the polynomial f is red? It means that it has at least two different remainders. Okay? But if we have a remainder 1, we have a sequence of elementary reductions leading to R1. Let's say that this sequence of elementary reductions goes through the first arrow. So this leads to R1. Okay? And I want to assume that this sequence of elementary reductions goes through, let's say, Fm. And these two remainders are distinct. Okay. Now, we want to use the assumptions of the diamond lemma. I want to apply these to the case of f, g1, and gm. Because of the diamond lemma, we can find a polynomial r and two reductions leading to the same polynomial r. Okay? And then we can proceed with the reduction such that we will get R3, which is also a remainder. So this is, because R need not be a remainder. That was exactly the question asked. And then we can reduce it further such that R3 is a remainder. So this is a remainder. And these guys are remainders. Now, let's take a look at the picture. F1 is a green polynomial. What does it mean? It means that every remainder of F1 is exactly the same polynomial. But by definition, we can reduce F1 to R1. So R1 is a remainder of F1. And also, we can reduce F1 to R3. So R3 is also a remainder of F1. So since this guy is green, we must have equality between R1 and R3. And exactly the same argument applied to Fm, since also green, leads to this equality. But now we have R1 is equal to R2, which contradicts to our assumption. So this is a contradiction. But where did this contradiction come from? It came from this assumption. The assumption that G is not a Gröbner basis. So that's why the assumption was wrong. So that's why G is a Gröbner basis. So this proves the diamond lemma. Okay. Who was able to follow the proof? Okay, are there any questions? Good. So this was the main ingredient of the proof of this criterion. So we slightly simplified the statement for the set G of being a Grobner basis. So instead of checking like all possible remainders, we just need to verify this simpler statement. Okay, but this is still very far from what's written here. Okay, what should be next? Now I need some auxiliary result, some technical thing. So, So what's written here? The statement, if I multiply and the difference. Okay. Well, a technical lemma, the claim. We have the set of polynomials and lexicographical ordering fixed. Then, suppose we can, okay, so G is a subset here, and F is a polynomial. Suppose we can reduce a polynomial F using G to a polynomial F prime. Here prime is just a name of the polynomial, it's not a derivative. And M is a monomial. Then we can reduce M times F to M times F prime. And the second thing, suppose we have two polynomials, N1 and F2, then suppose that the difference of these two polynomials can be reduced to 0. Then we can reduce these two polynomials to the same one. So if you want to prove that you can reduce two polynomials to the same one, it is enough to show that their difference can be reduced to 0. Because in a diamond lemma, this is exactly the statement that we want to check. So in order to check this, we will use this thing. So instead of checking that we can reduce two polynomials to the same one, we'll check that the difference can be reduced to 0. And why this is simpler? Because in this case, we have to find this R. Somehow we have to show that here it is. This is R, and then we should show that you can reduce these two polynomials to R. But instead of finding R, we can just check that the difference can be reduced to 0. So that's why it's simpler. You don't have to find some polynomial here. You just check that something can be reduced to 0. So that's why it will simplify the computation. Okay, now, who thinks that the first one is clear? Okay, is there anyone who doesn't think like this? Okay, who thinks that the second one is clear? Okay, and is there anyone who wants to see the proof of the second one? Okay. By the way, is there anyone who wants to see the proof of the first one? Because as I already know, if you know how to prove, it doesn't mean that you don't want to see the proof. Okay, so let's start from the first one. Suppose that you can reduce F to F prime. It means that there is a sequence of elementary reductions like this. And at the end of the sequence, we have F prime. So, and let me write down a monomial here, which was reduced in F. So let's say M1, M2, Mk. Now, let's take a look at one step of this process. So if we can reduce f to f1 using g1, and the reduction was done using the monomial m1 from f. So what happened here is we take f, we take g1, and we multiply it by m1 over the leading monomial of g1, and times some coefficient c, and then subtract this result from f. I'm not sure that it's large enough to see, but can you read this, or should I rewrite this? Okay. Yeah, it was impossible to see. Okay. So so by the definition, how reduction works? So we take a monomial from f, which is divisible by the leading monomial of g1. This notation means that this monomial is m1. So we took here m1, and it's divisible by the leading monomial of g1. Now we take g1 and we multiply it by a monomial in such a way that the leading monomial of g1 became m1. So we take m1 over the leading monomial of g1. So if I multiply this by this, then the leading monomial here will be exactly the same as m1, just by definition. Now, we want to cancel the term with the monomial m1. So we need to multiply by some coefficient such that the leading coefficient here is the same as the coefficient near m1. So then we subtract. So this is how the reduction works by the definition. Okay? But now, if we just multiply everything here by the monomial m, then we will get what? We will get mf1 equals mf minus c m1 over mg1 g1. But this simply means that we just reduced mf by the polynomial g1. The monomial that was reduced is m times m1, and the result is mf1. This is just by definition of the reduction. So that's why if we can reduce f to f1, then multiplying all these things by m, we get that we can reduce mf to mf1. So then we can proceed, so mf1 can be reduced to mf2, and so on, and in the result we will get that we can reduce it to mf prime. Okay? Good. Now, the second one. Suppose we have these two polynomials, we have this difference, and the difference of these two polynomials can be reduced to 0. So we have g1 to phi 1, g2 to phi 2, and so on. At the end, we will get 0. Okay? Now, this is by definition. What does it mean that we can reduce the difference to 0? It means that there is a sequence like that. Okay? Now, what I want to do, I want to show that if we can reduce this difference to phi 1, then what happens, we can reduce f1 using g1, let's say f prime 1, f2 using g1 to f2 prime, such that f1 prime minus f2 prime equals phi 1. So this is what I want. Okay? So if I can show this, then what does it mean? It means that I can represent this thing as the difference of two polynomials, such that f1 reduces to the first one and f2 reduces to the second one. And then I can repeat the argument in the same way, so the claim can be proved by induction on the length of this sequence. So this is the idea. Who was able to follow the idea? Are there any questions? Okay, now, suppose that the sequence has the length 0, which means that f1 minus f2 equals 0. It's already 0. So there are 0 reductions needed to get the 0 result. So in this case, well, you can take R to be F1 and F2, and this is how we're done. So, and if the length of this sequence is more than 0, then using this blue part, we reduce these guys to these two polynomials, and then by induction on the length of the sequence, we can reduce F1 prime and F2 prime to exactly the same polynomial. And since F1 and F2 can be reduced to these guys, we can prove the required statement using this blue part. So this was a reduction of the claim number 2 to this part. Now, how to prove this thing? Well, we should consider the reduction here. So F1 minus F2 leads to phi 1 using G1. And suppose we did a reduction of the monomial M. So the monomial M is presented here. So we may assume that the monomial here, the monomial M appears here with the coefficient A, and the monomial A appears here with the coefficient B. Now, the monomial M in the difference will be with coefficient A minus B. And since the reduction was possible, this coefficient A minus B is not 0, which means at least one of these two coefficients is also non-zero, because they both cannot be 0. Now, how the reduction should look like? Well, by the definition, this is F1 minus F2 minus G1, here M over the leading monomial of G1. And then I want to divide by the leading coefficient of G1 and multiply by A minus B. So this is by definition how the reduction works. So I take the initial polynomial, I multiply the leading the monomial G1 by a monomial in such a way that the leading monomial of G1 will be M, and then I should make the leading coefficient to be the same as the coefficient here near M. The coefficient near M is A minus B. The coefficient here near leading monomial is CG1, which is the leading coefficient of G1. So I should divide by this and multiply by this. So that's how I get the required leading coefficient. And now I can cancel what's given here. But now I can rewrite this as follows. F1 minus A over CG1 M over MG1 G1 minus F2 minus B CG1 M over MG1 G1. But what's written here is by definition a reduction of F1 where I chose this term to reduce. And this is exactly how the reduction works. And exactly the same thing happens here. This is exactly the reduction of F2 using G1, and we reduce this term. Now, I can denote this thing by F1 prime and this thing by F2 prime. So this means that we have what's written here. So that's how we complete the proof of the blue part. And this completes the proof of the second claim. Okay, who was able to follow? Are there any questions? Okay, now, just in case, it may happen that the monomial M is not presented here, which means that A is 0. If A is 0, it means that this expression is 0, so there is no reduction here, which means that, well, when I write things like this, I mean there are two options. Either F1 leads to F1 prime using one step of reduction, or it leads to F1 prime with 0 steps of reduction. For example, if A is 0, there was no reduction, so I mean it means that F1 equals F1 prime. So this is a subtlety that I didn't mention when I wrote this, but the subtlety explains the following thing. The length of this reduction and the length of this reduction could be different. Because you see, it may happen that you need one step here and just 0 steps here. So that's why the first, the first sequence will be shorter. Well, at least here it will be shorter. Okay. Now, okay, that was a technical result. And as I can see now, we are ready to prove the Buchberger criterion, which is written here. By the way, is it okay if I clear the central part? Okay, because I would like to start the proof of this claim using the whole whiteboard. Okay, now we're ready. So let me explain how we're going to prove this. First of all, we will prove that 1 implies 3. 3 obviously implies 2, and then 2 implies 1. Which one is the simplest one? No, there is at least one which is obvious. First one, which one? I mean, this? Exactly. 3 to 2 is obvious because what 3 says? It says that for every pair of polynomials, the S polynomial, every way to reduce S polynomial to remainder leads to 0. And this thing says exactly the same, but it says just one way leads to 0. Here, all ways go to 0, and there is just one way leading to 0. So if every way leads to 0, then at least one way leads to 0. So that's why 3 to 2 is trivial. So that's OK. Which one is the hardest one? Try to guess.
From the first to the third?
No, actually 2 to the
second to the 1.
Yes, from the second to the 1. Because since we want to check some huge property, and we want to check it using some like weak condition, so proving from weak to strong is the hardest. So let me start from the implication from 1 to 3. It's not that hard. So suppose G is a Gröbner basis. Now, so G is a Gröbner basis. And now we want to show that the S polynomial, every way to reduce S polynomial to a remainder leads to 0. OK. So let's take two polynomials, f and g, from G capital. Now, what is an S polynomial? By the way, who remembers the definition of the S polynomial? OK, so let me recall. So f consists of the leading coefficient, C1, the leading monomial, M1, and the tail, which consists of all the monomials that are strictly smaller than M1. G has the same form, C2, M2 plus G0. Then we should consider the least common multiple of the leading monomials, M1 and M2. Then we can represent the least common multiple as, OK, let's denote it by M, actually. Now, we take F, and we take G. Now we want to multiply F by a monomial in such a way that the leading monomial becomes M. So we should multiply by M over M1. And we want to make the leading monomial of G also to be m. So we multiply by m over m2. And now we want to make the leading coefficients here are the same. So we multiply by C2 here and by C1 here, and we subtract one from another one to cancel the leading monomials of these two polynomials. And this is, by definition, is the S polynomial. OK? Now, let's take this polynomial. So let's consider this polynomial. Now, we can reduce the leading monomial here using f. And it's clear that it can be reduced to 0. By the previous lemma, the polynomial f can be reduced to 0 by f. So that's why if we multiply it by some monomial, well, probably with the coefficient, then it also can be reduced to 0 by f. That's just the item number 1 from the previous lemma. From the other hand, the leading monomial here is the same as the leading monomial here, so it's divisible by g. So we can reduce it using g. And what's written here is the reduction of this polynomial by g. So the reduction of this polynomial by g leads to the S polynomial of f and g, just by definition. OK, who was able to follow what's written here? OK, are there any questions at this stage? OK, now let's take a look at some remainder of the S polynomial. So we can reduce it to a remainder. So we want to prove that every remainder is 0. So let's take an arbitrary remainder. But now, R is by definition is a remainder of this polynomial. And also 0 is by definition is a remainder of this polynomial. But since G is a Grobner basis, for every polynomials, every two remainders are the same. So these two remainders must be the same. So this proves that every remainder of the S polynomial is actually 0. So that's why if G is a Grobner basis, every reduction of the S polynomial leads to 0. Who was able to follow? OK. Any questions? OK, good. Now we want to prove 2 to 1. This will be an interesting part. OK, so if we want to prove this, we want to check that the assumptions of the diamond lemma are satisfied. So if we can check that the diamond lemma holds, then just by diamond lemma, G is a Grobner basis. So the idea is to use the diamond lemma. So use the diamond lemma. OK, so let's take an arbitrary polynomial f. And I want to consider an elementary reduction of f using g1 and an elementary reduction of f using g2. Now, what I want to show that we can reduce, so we don't know this. I want to show that we can reduce these two polynomials to the same one. By the previous lemma, item 2, it is enough to show that the difference can be reduced to 0. So now, we're starting from the polynomial f. We produced the polynomials f1 and f2, and we want to show that the difference can be reduced to 0. So now let's take a look at these two polynomials closely, and let's take a look what the difference is. OK, so by the definition, what was the reduction here? So when we reduced this thing, let's say we took the monomial F1, M1, and when we reduced this thing, we took the monomial M2. So by definition, F1 was what? It's G1. Then we multiply it by M1 over the leading monomial of G1. We divide by the leading coefficient of G1. We multiply by C1, and we subtract this from F. And the same thing happens with F2. This is F minus G1, M2 over the leading monomial of G1. We divide by the leading monomial of G1 and C2, where C2 is the coefficient near M2 in F, and C1 is the coefficient near M1 in F. These are just, by definition, these things. Okay? And now if I subtract F2 from F1, we can cancel F, and the result is what?
Isn't it G2 in the second?
What again?
Or F2, we reduced by G2.
Oh, thank you. That was a mistake. Yeah, exactly. So now, if we subtract F2 from F1, the difference will be C2 over C of G2, M2 over M of G2, minus C1 over C of G1, M1 over M of G1. Hooray! So the difference has the following form. It's a coefficient times monomial times G2 minus coefficient times monomial times G1. So this is how the difference look like. Okay? Now we want to show that this thing can be reduced to 0. So we want to show, so there is at least one way to reduce it to 0. It's enough to find at least one way. Okay. Now, well, let's take a look at this expression. So this expression is of the form coefficient monomial G2, coefficient monomial G1. So if I make a reduction of this expression by G1 or G2, the resulting expression will be of the same form, because every reduction, it subtracts G1 or G2 times a monomial and the coefficient. I'm sorry, no, it's not exactly this. Let me be more accurate. So let's start from the following thing. So let's take a look at the leading monomials of these two guys. So I want to take a look at the leading monomial here and the leading monomial here. So the leading monomial here is this thing, and the leading monomial here is this thing. There are two cases. The case number one, the leading monomials are distinct. And the case number two, the leading monomials are the same. Let's assume that the leading monomials are different. So if they're different, at least one of them is larger. So we may assume that this guy is larger than the other one. Well, in this case, what we can do, it means that the leading monomial of this guy is not cancelled. So it exists here, and it doesn't exist here. So the leading monomial of this guy, it's presented in the difference. So that's why we can take this whole expression and we can reduce this monomial by G2. So we can take this difference and we can reduce this monomial by G2. But what does it mean that we reduce this monomial by G2? It means that we just reduce the first summand to 0, Because, well, how do we reduce the leading monomial of this guy by G2? We just multiply it by lambda m and subtract. So that's why the reduction of this expression by G2 leads to minus mu times n times G1. But now, since this is a product of G1 times a monomial, we can reduce it by G1 to 0. So that's why if these two leading monomials are distinct, then we have found a way to reduce this difference to 0 in 2 steps. So this is an easy case. Now, the second case, when the leading monomials are the same. And there are 2 different subcases. The subcase number 1, we should take a look at the leading coefficients of these guys. And so what are the leading coefficients here? Well, lambda times the leading coefficient of G2 and mu times the leading coefficient of G1. So let's take a look at the leading coefficient of lambda m G2 and the leading coefficient of mu n G1. And there are 2 cases. The case number 1, they're the same, and the case number 2, they're not. Let's assume at first that the leading coefficients are the same. Then what does it mean? Well, if the leading coefficients are the same, then well, we just cancel the leading monomials which were here. But what does it mean that the leading monomials of G2 and, well, what does it mean that these leading monomials are the same? It means that m times the leading monomial of G2 equals n times the leading monomial of G1. So this leading monomial is divisible by the leading monomial of G1 and G2. So this is divisible by mg2, and this is divisible by mg1. So that's why it's divisible by the least common multiple. So is divisible by the least common multiple of these 2 guys. Okay, so I want to denote the least common multiple, let's say just LCM. Well, in this case, we can represent this monomial as D times LCM. And also, D actually divides M, and D divides N. Well, because LCM is this monomial times something, so D is just a part of this monomial, and also D is just a part of this monomial. Now, since this happens, what we can do, we can divide by D this expression, and we can rewrite this polynomial as follows. G2, G1 equals D times lambda M over D, G2 minus mu N over D, G1. Let's take a look at this expression closely. So what is the leading monomial of this guy? G2 times this thing. The leading monomial of this guy is M over D times the leading monomial of G2. M times the leading monomial of G2 divided by D is the LCM of these guys. So the leading monomial here is the LCM. Okay? And by the same argument, the leading monomial here is also the LCM. And the coefficients here were chosen in such a way that the leading coefficient here and the leading coefficient here is the same. Let's compare this with the definition of the S polynomial. How do we get the S polynomial? We multiply both polynomials by the monomials such that the leading monomials of these guys become the LCM. And then we multiply by by the special coefficients such that the coefficients of the leading monomials are the same. So this simply means, well, these leading coefficients need not be the same as here, but they are proportional to these coefficients because, well, the result leads to the same coefficients here and here. So that's why this thing can be presented as d times some coefficient c times the S polynomial of G1 and G2. So what we have shown here, if the leading monomials of these two guys are the same and the leading coefficients are the same, then this expression can be rewritten as the S polynomial times coefficient times a monomial. But now, just in case, who was able to follow this explanation? No? Who thinks that I should repeat the explanation? OK, so again, let me explain what's going on here. So we have this difference, OK? It looks like this expression, you see? What's the difference between this expression and what's written here? Well, here, these two monomials were chosen in such a way that the leading monomials of these two summands are the same, and they are equal to LCM. In this case, the leading monomials, in this case, of these two guys are also the same, but they need not be LCM. They could be higher. So that's why, so this is the leading monomial, and it could be higher than the LCM. So if I divide by some monomial d, and I can move it outside, then the leading monomials here and here will be LCM exactly as here. OK? But now, by the definition, the S polynomial, how to get the S polynomial, I should multiply this thing by C2 and this thing by C1, and then subtract one from another one. Then we will get the S polynomial. But here, well, the coefficients are not the one we needed. But we know that the leading coefficients of these guys are the same. Let's write them explicitly. What is the leading coefficient here? It's lambda times C of G2. And this is the same as mu times C of G1. OK? So let's rewrite this thing as follows. I will multiply this by C of G2, and I will divide it by C of G2. And the same thing happens here. I will multiply by C of G1, and I will divide it by C of G1. OK? But now, because of this equality, this fraction, lambda over CG, I'm sorry, did I did something wrong? Just give me a second. I should multiply by C1 here. I'm sorry. C1 here and C of G2 here. Just wrong. I just did the wrong thing here. So I just multiply by C of G1 and divide by C of G1, and multiply by C of G2 and divide by C of G2 here. And because of this expression, where I divided by this and divided by this, I see that lambda over CG1 is the same thing as mu over CG2. So I will denote this coefficient by C, and I also move it outside. And then let's take a look at what's written here. The coefficients here are exactly the coefficient that are presented here. So what's written inside is the S polynomial of G1 and G2. Is it clear now? OK, who was able to follow now? Good. Are there any questions, or probably should I repeat or explain at least something here? Good. But now because we're given the fact that for every two polynomials from G, the S polynomial can be reduced to 0 using at least one way. So we can reduce S polynomial to 0. And by the previous technical lemma, item 1, since we multiply it by coefficient with a monomial, we can reduce the same thing to this times 0, which is 0. So there is a way. So the case 2a was also considered. And now there is only one case when the leading monomials are the same, but the leading coefficients are not the same. So let's take a look at this case. I want to erase this part. Probably this one. So because we don't need this simpler part of the proof. So okay. And the last case is when the leading monomials of mg2 and mg1 are the same, but the leading coefficients are not. Well, in this case, this monomial is actually presented here because, well, this is the highest monomial of both summands. And since the coefficients are different, then it survives in the difference. So we can reduce this guy using which one? Let's say G1. So we can reduce this monomial using G1, for example. Let's do this. So, so we start with lambda m G2 minus mu n G1, and we want to reduce what? This monomial m n G1 using G1. So let's take a look what the result will be. So first of all, we want to rewrite the polynomial itself. Then subtract G1 times what? First of all, we want to make the leading coefficient, the leading monomial to be the same as the monomial we want to reduce. So we just multiply by n. Now we want to make the leading coefficient of this guy the same as the leading coefficient, as the coefficient here near this monomial. Well, first of all, we divide by the leading coefficient of G1 to make it 1. And then we just multiply by the leading coefficient here, by the leading coefficient here. But the leading coefficient here is the difference between this and this. So it will be lambda c of G2 minus mu c of G1. Okay? But now, you see, when you take this part of the fraction and this thing, they cancel each other because here 2 minuses, you will get plus mu n G1, and here minus mu n G1. So this thing and this thing, they cancel each other. But when you take a look at the result, you will get lambda m G2 minus lambda c G2 over c G1 G1 times n. Okay, now let's take a look at this expression. The leading monomial here stays the same. The leading monomial here stays the same. But the leading coefficients here and here are also the same, because here it's lambda times cg2, and here it's lambda times cg2 over cg1 times cg1. So the leading coefficients are the same, and we're in the case number 2a. But by this case, we already know, so by the case 2a, which is here, we know that this can be reduced to 0. And this completes the proof of the lemma. the claim. So again, let me explain what happened here. Yeah, so the whole proof.
Will this be in the exam?
Again?
Will this be in the exam?
Yep. Yep. That will be a part of the exam. That's the best part of it.
So someone is very unlucky.
Well, it depends how you understand the meaning of lucky. Because, probably you made the wrong choice. That's not the best place for you to be at the first place. And somehow you come to the exam, you just take the diamond lemma, the Buchberger criterion, and all of this stuff. You look at them and you're, okay, I wanted to be an artist all of my life, so I have to change my profession. So probably this means that you're lucky. Okay, so let me explain the whole proof again. So that was the beginning of the proof, and this is the end of the proof. So what we did, we started with the item number 2. So for every 2 polynomials, the S polynomial of f and g can be reduced to 0, at least in one way. Then g is a Gröbner basis. What we did, to check that g is a Gröbner basis, we need to check the assumptions on the diamond lemma. And in this case, we take a polynomial f, we take 2 reductions of the polynomial f, and then we want to find a reduction of f1 and f2 to the same polynomial r. Instead of doing that, we take the difference between f1 and f2, and we want to show that there is at least one way to reduce this difference to 0. And now we just write down this expression explicitly, just by definition. We just consider the most general situation, what happens here and here. And when we rewrite this difference, it's presented in this form, where coefficients monomial g2, coefficient monomial g1. And now there are 3 cases. The case number 1. So let's say, what can prevent us from doing a reduction? Well, for example, it's clear how to reduce one of them, because it's just the previous lemma, item number 1. So it's clear that this summand can be reduced to 0 and this summand can be reduced to 0. So why it may happen that the difference cannot be reduced to 0? So what's the reason why this thing can be reduced to 0? Because the leading monomial here can be reduced. And what is the reason why this guy can be reduced to 0? Because the leading monomial can be reduced. So what terrible may happen when you take the difference is that the leading monomials, they can cancel each other. So that's the issue. So that's why we should take a look at the leading monomials. And the option number 1, they're different. And when they're different, well, it's easy to find a 2-step reduction to 0. And the case number 2, when they're the same. And when they're the same, there are 2 options. If the leading coefficients are the same, the leading monomials cancel each other. And if the leading coefficients are not the same, the leading monomials, they do not cancel each other. In this case, since the leading monomial survives in the difference, we can reduce it, let's say, by g1. And this reduces this case to this one. But in this case, because the leading coefficients and the leading monomials are the same, we can rewrite the whole expression as the S polynomial times some coefficient and monomial. And the fact that we can reduce the S polynomial to 0 by at least one way sequence of reductions is just given to us by the assumption. So that's why the whole statement works. OK, who thinks that he was able to follow the whole proof? More or less. OK, good. So we have 10 minutes. Do I have enough time to prove that the Buchberger algorithm stops? I believe yes. You don't believe in me? OK. That's the talk. OK. Okay, the claim. Probably it's called Dixon lemma. Okay, I'm not 100% that the surname written correctly, but I will take a look at the notes. Well, suppose we have a sequence of monomials. And if you take I smaller than g, then mi doesn't divide mg. So we have like a sequence of monomials, and if you take two guys, the guy that appears earlier, it doesn't divide all the guys that appears after this one. Then this sequence is finite. So it's impossible to find an infinite sequence depending on finitely many variables. So we have finitely many variables, let's say x1, xn. So you see, I want to show that the Buchberger algorithm stops. So I have to show that some process will terminate. So this is exactly what happens, that if I have a process of producing this kind of monomials, it will terminate. So that's why it will be useful to prove that the Buchberger algorithm stops. OK, so let's prove this. Well, what does it mean that mi doesn't divide mj? Oh, by the way, no, before doing that, I want to say some general words. We will prove by induction on the amount of variables. So induction on n, the amount of variables. So suppose n is equal to 1. In this case, we have just x to the power of k1, x to the power of k2, and so on, x to the power of kr, etc. What does it mean that x to the power of ki doesn't divide x to the power of kr? It means that ki is greater than kr. So we have a strictly decreasing chain of powers of a variable. So that's why it must be finite. So in case of n to be 1, it's just simple. So now we want to show that if we can prove this for n variables, then it can be shown for n plus 1 variable. Then it will be true for all amount of variables. Now, what does it mean that mi doesn't divide mj? It means that there is a variable, let's say xs, such that the power of mi is larger than here. So the power of xs in mi is greater than the power of xs in mj. Give me a second. How should I proceed further? Now I want to use that there are infinitely many monomials, but finitely many variables. But I want to be strict. Give me a second. Should I start just with m1 or not? Okay, so yep. So now I want to take m1 and all the monomials here. So for each monomial here, there is a variable such that mj has a power less than the power of m1 in this variable, okay? But there are infinite, so for every monomial, we just write down this variable, okay? So we have the sequence of monomials, m2, it has, and so on. But now, this sequence is infinite, but there are finitely many variables, which means at least one variable will appear here infinitely many times. So at least one variable, so let's say x n plus 1 will appear infinitely many times. So that's why I can drop all the other monomials, and I may assume that when I consider this sequence of monomials, then the degree of m1 in the variable xn plus 1 is greater than the corresponding degrees in all of these monomials. So d1 is greater than d2, etc., dj, and so on. It doesn't matter. Well, okay. Okay. You're right. So you're right. Still, it doesn't matter, because it's just the question of one integer. But yeah, formally, you're right. You're right. But if it's strictly larger, then it implies that it's just larger. It's not smaller. So formally, my claim was weaker, but still true. But it doesn't matter. Let's assume that this holds. But this means that the sequence of the degrees is the sequence of integers which is bounded from above. So this sequence has finitely many values. So that's why there is a subsequence consisting of the same value. So because of this, so these guys, they can be between. So these guys, they may have values between 0 and d1 minus 1. Since this sequence is infinite, at least one of these numbers may appear here infinitely many times. So let's let's take this subsequence. When we drop all the other terms of this sequence, we may assume that now we have this sequence of monomials such that starting from m2, we have the same degree for the variable xn plus 1. But by the hypothesis, every monomial with a smaller index doesn't divide every monomial with the larger index. Since we just passed to a subsequence, the same property holds here. So, but this monomial is represented as what? m2 of x1 xn times xn plus 1 to the d. Then m3 x1 xn times xn plus 1 to the d, and so on. So what does it mean that this thing doesn't divide this thing? Well, it simply means when we drop xn plus 1, the remaining part doesn't divide this thing. Because if this guy divides this guy, then the whole monomial also divides the next one. So that's why we can pass to a sequence of monomials depending on the smaller amount of variables. And by the procedure, we started from an infinite sequence of monomials. So that's why this sequence is also an infinite sequence of monomials, but depending on smaller amount of variables. And by induction, this sequence must be finite, and this is a contradiction. So this must be finite, and this is a contradiction. Contradiction with the assumption here that the sequence was infinite. Who was able to follow? Are there any questions regarding this part? Okay, now I have like 0 seconds to prove that the Buchberger criterion Buchberger algorithm terminates. By the way, who remembers the algorithm? Okay, let me recall the algorithm. No, it will be easy. Now it's just like, give me 2 minutes. Well, we have a subset of polynomials. Let's say without 0, and we have a lexicographical ordering fixed. Now, what we do, so the step number 1, we take all the possible pairs of polynomials from G, and we produce all the S polynomials for all possible pairs. Then we consider a reduction of this pair. Now, if all the remainders are 0, then this is a Grobner basis. If not, then we add all the non-zero remainders and just repeat the procedure. Okay? Now, we want to show that this procedure will terminate. Okay, if it doesn't terminate, it means that at each step we will add at least one new remainder. Let's take a look at the sequence of these remainders. Well, what does it mean that we are given a remainder? Well, let's say we have G, then we added a remainder on the first step, then we added a remainder on the second step, then we added a remainder on the third step, and so on, okay? Now, let's take a look at the sequence of these remainders that were added. At least one remainder was added at each step. Now, if this is a remainder, it means that every monomial of R2 is not divisible by the leading monomials from here. So at least the leading monomial of this guy is not divisible by the leading monomial of this guy. So if we take the leading monomials of new remainders, it satisfies this property. And since a sequence of monomials with this property is finite, this procedure will terminate. That's it. Yeah, so that's it. Well, guys, thanks for being here. That's the final lecture. I hope that was at least interesting. Thanks for being here during the whole module.